All right, welcome to lesson 4.8 notes, advanced algebra, analyzing graphs of polynomial functions. Sounds crazy. It's the last lesson of the chapter, of chapter 4. It's a good summary lesson. It puts a lot of skills together, not as much as some of the other ones. I actually think it's a good way to finish. It's not, I don't think, overly taxing, although you still have to be able to call back some of the stuff, some of the other graphing skills that we've built now over the last couple really chapters. So I think let's just jump in. Let's get it going. It's not overly long. I cheated a little bit, and I plugged in some points to try to make the video right. I did a lot of the calculations already, so we don't have to sit around and listen to me type numbers into a calculator. It's boring enough watching me do it in class, but if you're just listening right now, whatever. I'm already rambling. Let's go. Here we go. First concept. We've talked about this a lot. How all of these things, whether we're talking about a zero, a factor, a solution, or an x-intercept, for us, they are definitely not exactly the same, but they are really, really, really related. Okay. It all kind of depends on just what situation we're talking about. You know, a generic function like this, if it's f of x equals some, could be all sorts of stuff. But when we talk about the function itself, we'd say find the zeros of that, and that's us setting the function equal to 0, and it essentially finding the solutions, right? Zeros and solutions, I feel like we used quite a bit interchangeably on some level. How do we find those zeros or those solutions? Usually we set this equal to 0. I guess I shouldn't say usually, but a lot of times we will factor this, write it as factors, x minus whatever, to find your solution. And then a lot of times we end up using those solutions, those factors, those zeros to make graphs, because those are points in our graph as x-intercepts. So hopefully that makes sense. I know maybe that wasn't the greatest there, but over the course of the last chapter or two, we've used these terms a lot. I guess for today's lesson specifically, it's x-intercept. The solutions, the zeros that we find, we're going to use as x-intercepts, as points on our graphs. Okay, so that's kind of the big just setup, I guess, for today's lesson. I set this up. You're welcome to kind of add it to your notes. A lot of it we've talked about already. There's a few new things, so maybe just hear it. I'll talk through. I won't spend forever on this slide because we'll kind of do it as most of you can see here. Example 1, 2, and 3 all involve just making graphs. Basically, we're at a spot where we can make fairly detailed graphs beyond just kind of plugging in random numbers, right? Maybe coming into the course, if that's all you knew was that actually isn't. I mean, that's part of what we do. Is we're still in the end at some point going to have to plug numbers into a function, but we can use some of our skills such as factoring, such as the just touch or pass through concept, the shape hands up, hands down, hands opposite, degree leading coefficient. So we can we've learned a lot of stuff beyond just plugging in points. So basically, how does it work? You plot the x-intercepts, you start there. Sometimes we'll be able to jump right to it. So today, I think the first two graphs I give you are already factored, so that's awesome. We're going to plug points in between the x-intercepts. Sometimes there's more, sometimes there's less. It all depends on how close your x-intercepts are together. Beyond means just one outside, one to the left and one to the right of your your x-intercepts. And I'll ask you for your y-intercept. That's always going to be us plugging in 0 for x. Okay. Usually when we're finding our degree and leading coefficient, when the polynomial is written out like this, x to the third minus 2x squared plus 4x plus 3, whatever. If it's written like that, hopefully everyone can look at that and say, oh, yeah, that's odd. And my leading coefficient is 1. That's positive. That's a left to right, positive slope, opposite direction type of graph. We haven't seen as much when it's written like this. Say, well, what the heck? So the leading coefficient is still right out front. It's still, in this case, 1/6. If there was no number there, it would still be 1. But when it's written as factored form like this, how do I tell what degree is? And obviously you can read my note here. It it's third degree. The short answer, the informal answer, is just basically add up your exponents, right? I got an exponent of 2 right here. The hard part is maybe people forget that there's an exponent of 1 right there. So if I add my exponents up and say 2 plus 1, that's really where the third degree is coming from. The little more formal way to think about it is how many factors does it have? X plus 3, x minus 2, and another x minus 2. So there's 3 total factors. That's 3x intercepts. Well, in this case, 3x intercepts. Really more, that's what makes it third degree. Okay, so we'll practice that with these first couple where we'll see them factored like that, and we'll have to come up with the degree and behavior and shape. The last part is, I guess I should say in here at some point, we should identify that, a just touch x-intercept, like this one right here. It's an even repeater, so my graph is just going to touch at the 0.20 there. But then, in the end, you're going to add a smooth curve and connect them left to right that matches your end behavior. So let's jump in there. Let's do a couple here. Let's see what we got. So graph the function. So the first, I think, big difference that we've seen, which I think ends up making things quite a bit easier, is it's already factored for us. So stuff that I would be looking to do here that I'm going to do is, all right, I see my leading coefficient is positive, whether it's a fraction, it doesn't matter. It's positive, and my total degree is 2 plus 1. So this is third and even, I'm already screwing up. Third, which is odd, basically. It's third degree. Let's just write that. Third degree, which is odd. And my leading coefficient is positive, so my shape should take on that shape, left to right. So that's the first thing I think we should probably do on any one of these graphs, is identify the end behavior, left to right, hands up, hands down, or hands opposite. From there, the next thing that I think the easiest thing to do is look at your x-intercepts and say, hey, you know what makes this equal to 0? -1. So that means -1, 0 is one of my x-intercepts. It's a point on the graph that we can throw on there right away. I've got what makes this equal to 0, 4. So the point 40 is also on my graph. 1, 2, 3, 4, 0. So I start with your start with your shape, go to your x-intercepts, especially if it's already factored like this. It's already factored, it's great. I would you don't necessarily have to tell me, but I'm just right now, for the sake of teaching the lesson, I'm gonna make a verbal note. You could make a mental note of saying, hey, this one right here with this even repeater, that's gonna be a just touch. If you're like, what the heck is he talking about? That either means you were gone or you don't remember. Go back and watch. I think it was day 1 of the 4.5 notes, just touch. So we're just going to touch right here as I'm coming through. I must turn around and then get up over here. So I basically already know what this graph's going to do. It's going to come in low on the left because of my shape right here. Low, just touch right there. It's got to turn around here somewhere. It can't cross anymore because I've got all 3 zeros accounted for, and I'm up and through that point right there. So everything else now is plugging in points. You have to tell me your y-intercept. So that's going to come in by plugging in a 0. I did this already. It's 0, -1. Okay, this is just me. Again, I said at the onset there, but I hopefully didn't skip over that part. I've done all the calculations here, so this should hopefully go quick. But there's no secret. I'm actually plugging these numbers in the calculator. I just did them beforehand. So 0, -1. Okay, great. So now the last part, the directions on the homework on a quiz would say plug in points between and beyond. So this one ends up kind of being a long one because if I'm talking beyond, so where are my x-intercepts? Right here and here. I need to go beyond. So one x this way. So that's -1. That means I should do -2. Okay. And then beyond this way, if that's 4, I should go 1 this way, 5. Okay. So -2 and 5. So you understand what that means when I say beyond? It means to the left and to the right of your furthest left and your furthest right x-intercept. Okay. So when I plug those in, let's check my little cheat sheet. When I plugged in a -2, I got -1.5. And here is basically just to make sure, let me plot it so I don't screw it up. And then if I plugged in the 5, what do I get? 5, 9, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, way the heck up here. But basically, that part is just to kind of make sure, it's almost like a double check to make sure that we're lining up with what we think is going to happen. I knew that was going to happen, that it was going to come in low. That's matching up with what I thought was going to happen. And it's going to, we said it was going to finish high. So, yep, it's going to finish high over here. The last, oh, let me write that down, 9. What makes this one a little bit longer than some of the other ones is that the between the x-intercepts, I've already got the 0 done because that was a mandatory y-intercept. But I end up with, there's a 1, 2, and a 3, some x-coordinates in between these ones. So it is what it is. In this case, I end up having to plug in, I should plug in 1, 2, and 3. Just because those are x points between my x-intercepts. 1, 2, and 3. So yeah, figure it out. I think at this point of the year, hopefully everybody's solid with their calculator work, and you can kind of, depending on your model, obviously you might have to some of us might have to retype the whole thing, but hopefully you can find an efficient way to do it. I got -3, 1, -3, it's almost 2, -4.5, and then 3, -4. If I put them on there, hopefully 1, 2, 3. 2, 1, 2, 3, 4.5, and then 3, 1, 2, 3, 4. Yeah, I mean, the graph almost builds itself. We're doing a lot there. So let's finish it. Let's sketch the graph. Smooth curve. We said this was going to be a just touch right here. I'm left to right hitting all of them. Bottoming out there, and I know it's going to skyrocket off my page. So it's basically, this is as detailed of a graph we've ever made. Obviously, this one probably has the most points we've ever put on a graph. 1, 2, 3, 4, 5, 6, 7, 8 points. That's probably one of the highest ones. They're not all like that. I think the next couple we can get by with like 5. But it kind of just depends on where your x-intercepts are. So yeah. That's the general idea, using the x-intercepts. Let's look at another one. It's similar. I know the shape, I think, ends up being the same. So let's just take from the top. This is one that, okay, if I start from the beginning, what am I looking at? The first thing I'm going to do, slow down, Mr. Crow, just talk regular speed. Add up your exponents here. So these are all first degree. You could say there's 3 total factors. That's what makes this third degree, which is odd. So I know it's going to be either this or this. I look at my leading coefficient, it's positive, so that narrows it down. It's got to look like this, so it's going to look just like the shape is going to be similar to the last one. Where this one's kind of nicer, well, let's see. They're all individual, all 3 are different, I guess. There's no repeaters. So I've got the point 2, 0, the point -1, 0, based off of that one, -1, 0, and the point 1, 0, based off of that one. So no repeaters. These should all be passed through because they're odd. Now, where this one's, I think, also different is look how close these are together. There's not really a whole number in between here and here. We said the y-intercept was mandatory, so you're going to do that regardless. Even though you're kind of doubling up, it's technically in between these 2 x-intercepts. But we had to do it anyway. So when I plugged in a 0 there, I got 0, 4. 0, 1, 2, 3, 4. And then I think my betweens are all done, right? So that's kind of nice. This one's as short as we've done. I plugged in 1 number there. I'm going to plug in 2 more. So beyond this x-intercept is 1 more x this way, which would be -2. And then a beyond this way would be 1, 2, 3, an x value of 3. Those are the only ones I need. Sweet, 3 total points. So if I plugged in a -2, I screwed it up the first time, so I'm hoping this is right. -24. And if I plug in a 3, I'm ending up with 16. And I think that has to do with this being a 2 out there. It gets pretty steep pretty quick. So obviously both of those are way, 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 way off the page. -2, 24 would be like way down here, probably even lower. And then 3, 16 is way above that. So It lines up with my shape. I'm not going to get any extra points, but I guess basically this should be coming in like super steep. These are all pass-throughs, we said. So we're not going to turn around. I could look, at what's going on here in between. So I know it turns around somewhere in here. So if I was going to be like super accurate, I would say, well, could you go in between these two x-intercepts and do like a 1.5? Absolutely. I think on the next one I do something like that. But I know it's got to finish high. Whoops, I didn't mean to do that. Right, based off of this right here. And I want this graph to turn around and it's confirmed by the 316 way up there. So I need to turn around at some point and get skyrocket steep up to that right there. Arrow on both ends. So you go from one where you plugged in 8 points to one where I ended up actually only plugging in 3 points. These were basically free. Okay, so putting a lot of those skills together. I think like probably the most involved ones we see next. Really, it's the last graph of the lesson. Look at that. We got one graph left, one note, and then a shorter example where the graph's already done for us. So let's see. Let's do it. Let's keep her moving. We're doing good. All right. What makes it tougher potentially is, oh no, it's not factored. So when I say, hey, what are the x-intercepts? I don't know, right? Where these ones we were able to look at and say 2, -1, 1. That was simple, right? So here, there are a couple nice things I get though, okay? So hopefully, again, going back a couple chapters, we can look here and say that's third degree, no question. Like it tells me it's third degree. My leading coefficient is positive. Maybe I should pick better examples, but it is what it is. It's now 3 times in a row. But that part I would say is easier to recognize. Third degree, leading coefficient positive, low to high, left to right, good. The other nice, you don't get a lot of nice stuff here, but you do get your y-intercept. If I plugged in a 0 for x, which is how we do it, that would cancel, that would cancel, that would cancel, which would just leave us with 2. So 0, 2, okay. I get kind of 1 free point. It's not the greatest, but it is what it is. I got something. I also think maybe the plug-in here is something we're a little bit more used to, where it's plug-in and use parentheses on your plugins, but I'm plugging in the same x value, those 3 spots. So at this point, I guess the next thing we got to look at is what are the x-intercepts? Okay, where is that going to come from? I need to factor this thing. Okay, now that could be true factoring, which I think this one here, I'm just going to come down here so I have a little space to work. True factoring, by that I mean if it's a 4-termer like this, I might look to, which I think is going to work, a factor by grouping. I could potentially, if it was a 3-term polynomial, I might 2 numbers that multiply to this, that add up to this. Difference or sum of difference of cubes, sum of cubes, difference of squares, which I think we'll see here. I could also have to like synthetic divide to check possible zeros. And so this could be longer. I don't think I ever have them go super terrible where you're doing extended, but you'll see on the homework, there's a little space to do some work here. So anyways, let's do it. What are we going to do? We're going to look at this right here and say, hey, I can factor this by grouping. Hopefully we see stuff like that. I see this first group. If I take out an x squared, that leaves me an x minus 2 right in there. I know this has got to be x minus 2 if I reverse engineer it, meaning I got to take out just a -1. I put these two things together, x squared minus 1 and x minus 2. And then I see, oh, wait a minute, this is a difference of squares again. That one's got to get another round of factoring. So x plus 1, x minus 1, and then we still have the x minus 2. If you need help with that, you got to go back and look way back. Actually, not too far back, 4.4 notes. So yeah, now we're basically picking up right there where the last 2 examples started. Right, I can look at that. Hopefully, everyone else can look at that and say, "Hey, I can see I've got an x-intercept of -1, 0, 1, 0, and 2, 0. Which, kind of like the previous graph, these are all right next to each other. Negative 1, 0 is right there, 1, 0 is right there, and 2, 0 is right there. So yes, it was more work. We had to factor. But I think on the plugin, we end up kind of like the last one where in between, there's nothing there. You know, we've got everything. They're consecutive integers. We're fine, I think. I'd be totally fine with if we just wanted to jump out to finishing with, okay, plug in a beyond to the left and negative 2. Plug in a 3 because that's beyond to the right. What do we come up with? Negative 2, negative 12. And then if I plugged in the 3, I got 8. Now, again, I did it beforehand because we're going to see, well, we'll see here in a second. If I go to plot these negative 2, negative 12 still off the graph, even though I changed the scale here a little bit, it's fine. 3, 8. 1, 2, 3, 4, 5, 6, 7, 8 is up here. It matches up with our shape. I'm starting low. These are all pass-throughs. There ended up not being any even repeaters, so they're all pass-throughs. So pass through, flip around. I got to pass through here. Now, this is the part I was talking about. If I wanted to actually see where does this happen, where does this flip? So I did it just so we could kind of see for the notes here. I plugged in a 1.5 just because that's in between 1 and 2 here. And it's actually really small. It's negative 0.625. So this barely goes underneath there. Now, if you didn't do that, that'd be okay because you would just turn around somewhere in between there. Maybe you dip like that. And you say, hey, I got to get back up to 2 real quick. And then we skyrocket off the page. So it would just be more of a, if you're not sure what's going on there, because sometimes I will see people do weird stuff where they, with these 2 in a row, I don't know, they do like that stuff. And then that's bad, obviously, so if you weren't sure, you could always plug in an extra point there and double check it. Yeah, so that I think you got the idea by that point. What was it? It was negative, if you wanted that one. But basically, yeah, follow kind of the game plan there. Factored if it's not factored, identify your x's, x-intercepts, your shape, your y-intercept, and then when in doubt, plug in more points than less. Beyond, in between for sure. So there you go. We'll be fine there. I think people usually do all right. Last concept of the chapter. Sweet, awesome. Turning points. So this can be like a new section in your notes. Turning points. I've actually I think said it a few times. It's where the graph turns over, right? Where you're going up, 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 up from left to right, up, 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 and then I kind of flip, and all of a sudden I'm going down, 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 down. I'm going back up, 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 up. Those are called turning points. Pretty generic. What we do need to know, okay, and identify, which isn't, I don't think, that much to ask. Those turning points have a specific name. They're either going to be a local maximum or a local minimum. Okay, it's not the true, so like this point right here, it's not the true maximum of the graph, right? Like this graph goes way up here, it goes up forever and ever and ever. So there is actually no total maximum of the graph. It approaches infinity. But in this area, think locally, this is the maximum because you get up to this tip top point and then we start going down again. And then exact same thing going on here, except with a local minimum. This isn't the true minimum of the graph, but it bottoms out here. We turn over, we're going down, down, down. It doesn't get any lower than this in this local area right here. So that's what we would call a local minimum or local maximum. So basically, I'm going to ask you to identify those on your graph. We could go back to any one of the graphs we've made and say, hey, you know what? This right here is a local max. That right there is a local min. Okay, not a big deal. I think pretty easy to wrap our heads around. Plural, I think you'll see it here, local maxima, local minima. It's just the plural version of maximum and minimum. Okay, so that part should hopefully be no big deal, more of just a vocab thing. Last part for your notes here, It's still in the turning point section. That's why we're all on the same slide. Sometimes a little bit tougher. You can write these, I think. It's basically the degree of the polynomial. If I subtract 1 from the degree, so let's say I got a 5th degree polynomial, whatever, x to the 5th, blah, 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 plus, whatever. That graph has at most 5 minus 1 turning points, so 4 turning points. Okay, so basically what's going on there is you could look at the degree, 5, 6, whatever, 10, and say, okay, that graph, without even seeing it, has at most the degree minus 1 turning points. Okay, it could have less. It could have this doesn't have to automatically have 4. Maybe it only has 1. No, I'd probably have to have at least 2. But anyways, at most it could have 4. Okay, and then this one it goes right along with that. If you know the graph has n distinct real zeros, so let's do one that actually has so this graph has 3 different real zeros. Distinct meaning different. 1, 2, 3. This graph has 3 distinct real zeros. Then its graph has exactly n minus 1 turning points. So if this is holding true, that had 3 distinct real zeros. Real, that's important too. Then it should have 3 minus 1 turning points or 2 turning points. Let's check. 1 turning point, 2 turning point. That was it. So it had 3 distinct real zeros, not imaginary. It would have actually exactly 3 minus 1 or 2 turning points. We'll see here. Basically, what am I going to ask you to do with it? Either after the fact, after you graph something, identify your local maxima or minima, plural potentially if there's more than one. Or in this case, here's a graph. Sweet, I don't have to build the graph. This is our last example. It's kind of a vocab check to start, but then tell me what's the lowest degree. Determine the least degree that this could have. We'll finish with that part, okay? Let's knock out this first part. Here's how you can do this. It says, estimate the coordinates of each turning point, and then state whether each corresponds to a local max or a local minimum, okay? So here's how you can do this, and you can do this on the homework too. You can just put you can put points there and call it just because it gets really tight if I try to write all that stuff on here. So like point A, it tells me first estimate the coordinates of each turning point. I spoiled part of it. Like those are the turning points, right? 1, 2, there's 3 total turning points here. So what are the coordinates of this point A right there? Negative, going by 2, oh no, go by ones. Negative 1.6, 1, 2. And that's an estimate. So if you said negative 1.5, you're okay. It's just me testing you to see, do you know like what a turning point is? Okay, yep, that's a turning point. Is that a local maximum or a local minimum? A would be a local minimum. That's like the bottom out right there. So local, say local though. I feel like I've said it so many times it's lost meaning. Local min. You can abbreviate there. All right, one down. Let's go to B. Can we get all the colors involved here? Let's see. B, what are the coordinates at that point? That's like negative 0.5, negative 0.3. Oh, is that going to bother you? It went left, half, down, third, 0.4. Okay, that would be a local max. We got one more. Point C. Point C is definitely gonna be a local min. What are we talking here? Let's go like 0.75 to the right, so 0.75, and then down 2 again. That's a local min. Pretty doable. Did we do that? Estimate the coordinate. Oh, I don't want to do that. I was trying to write over the top. Estimate the coordinates of each turning point, done it. State whether each is a local maximum or a local minimum. Look at that, we crossed off so much. Estimate all real zeros, okay? So that's still checking vocab. Do you know that this right there would be a real zero and that right there would be a real zero? Let's call that points D and E. So I'm basically also checking, do you know that zeros mean x-intercepts? Real zeros mean x-intercepts. So D would have the coordinates, let's see, that's almost 2, a little bit past though, -2, let's say -2.1, 0. That's going to be automatic 0. And then, let's see, what color am I use here? Regular purple. E, a little bit beyond 1, so 1.1, let's say, 1.10. Estimate all real zeros. We've done that. And here's that last part. Determine the least degree this function can have. So that's like reversing this basically. At most, it can be this degree if I know the degree of it. Like if I know the degree of the polynomial, it has at most this many turning points. So this is now the flip. If I can see that this graph has 1, 2, 3 turning points, I actually have to add 1, right? Because this said if you knew the degree, subtract 1 to find the turning points. So this could not be a first, second, or third degree at minimum because there's 3 turning points. This has to be at least 4th degree. Okay, minimum. Can I tell you exactly? No, because I can only see there's only 2 real zeros. That means there must be at least 2 imaginary, but you could have, maybe 4 imaginary ones that we're not seeing. Obviously they don't show up as x-intercepts. So imaginary zeros are not going to be x-intercepts. They're kind of involved with what's going on here a little bit. So all in all, hopefully that's a very doable just type of problem there. This section in general, hopefully that's something we can do and do well. So I think that's it. I mean, obviously it was kind of just the one big goal. It was kind of loaded. It was graph polynomial, identify the x, y intercepts, local max, local mins, minimums. That looked wrong. Anyways, I think we're good. Let's wrap it there. Let's say we're good. Lesson 4.8 in the books. I will see you in future lessons.